Theorem 14.1 is called the conjugate zeros theorem, and it is going to be a continuation of example 14.2, where we notice that the irrational and the complex zeros always appeared as a conjugate pair. So the first statement says if a plus the square root of b is a zero, then a minus the square root of b is also going to be a zero. This is known as irrational conjugates. And statement number 2, let me fix that, it should say a 2 there. If a plus bi is a 0, then we can also say that a minus bi is going to be a 0. This is known as complex conjugates. Now, the reason why we always have the pair of conjugates when we're dealing with irrational and complex is because of how the irrational and complex zeros arise in solving a polynomial equation. They always appear because we have to take the square root within a equation. And when we have to do a square root within a solving situation, that means that there will be a plus or minus accompanying that square root. So therefore we get the two different answers, one with the plus and one with the subtraction. So then example 14.3 gives us a chance to practice this. It says complete the following statements. If 3 minus 2i is a 0, then what also has to be a 0, and that would be 3 plus 2i. And second statement, if negative 1 plus the square root of 7 is a 0, then what else is also a 0? That'll be negative 1 minus the square root of 7. So we will see conjugate pairs come back to play in section 5 when we start talking about the linear factorization theorem and the ability to be able to write a polynomial equation for ourselves.